Professor Shivkumar Balagaon, working as an assistant professor in the Department of Humanities and Sciences, Walchand Institute of Technology, Solapur. In this video lecture, we are going to learn about the concept of Fourier transform with the help of some examples. The learning outcome of this concept of Fourier transform will be, at the end of this session, students will be able to understand and determine Fourier transform of non-periodic functions. Now let's go to the definition of Fourier transform. Fourier transform of the function f of x is given by integral from minus infinity to infinity e to the power minus I lambda x f of x dx. We use capital F of lambda notation to denote Fourier transform of the given function, where lambda is a real or complex parameter. Here in this definition, the exponential function e to the power minus I lambda x is also called as kernel of the transformation. The importance of Fourier transform lies in the fact that it's a very effective and impressive mathematical tool which we use to transform the non-periodic functions from time domain to the frequency domain. Now let's understand the use of the definition of Fourier transform to solve some examples. The first example is, find the Fourier transform of f of x equal to 1, where x is from 0 to 1 and the value of the function is 0, otherwise means from negative infinity to 0 the value of the function is 0, and from 1 to infinity again the value of the function is 0, and the value of the function is 1 in between 0 and 1. The solution of this problem, we will start with applying the definition of Fourier transform to the given function. We get f of lambda equal to integral from minus infinity to plus infinity e to the power minus I lambda x f of x dx. Putting the value of the function in this definition, we get f of lambda equal to minus infinity to 0 e to the power minus I lambda x f of x dx plus 0 to 1 e to the power minus I lambda x f of x dx plus integral from 1 to infinity e to the power minus I lambda x f of x dx. Here the integration has been splitted into three different integrals depending on the definition of the function, because the function is defined to be 0 in the interval minus infinity to 0, and the function is defined to be 1 in the interval 0 to 1, and the function is again defined to be 0 in the interval 1 to infinity. Now we just have to substitute the value of the function in this step. We get f of lambda equal to integral from minus infinity to 0 e to the power minus I lambda x into 0 dx, because the definition of the function in the interval minus infinity to 0 is 0, therefore we have put 0 here, plus integral from 0 to 1 e to the power minus I lambda x into 1 into dx, because the value of the function in the interval 0 to 1 is 1, plus integral from 0 to infinity 1 to infinity e to the power minus I lambda x into 0 dx, because the value of the function in the interval 1 to infinity it is again 0. Therefore simplifying, we get f of lambda equal to integral from 0 to 1 e raised to minus I lambda x dx. Now to evaluate this integral, we need one basic integration formula. So recalling it, the formula of integration required is integration of e raised to ax dx, which is equal to e raised to ax upon a plus c. Plus c is written here because the formula is of indefinite integration, and here we are dealing with definite integration. So there is no question of writing plus arbitrary constant. So using this formula, we get f of lambda equal to e raised to minus I lambda x upon minus I lambda. The limits are 0 to 1. Now putting the upper limit and the lower limit in this step, we get f of lambda equal to x equal to 1 is our upper limit. So putting the upper limit, we get e to the power minus I lambda upon minus I lambda, and then minus of lower limit substitution gives us 1 upon minus I lambda, because e to the power 0 is 1. Now simplifying it, we get f of lambda equal to 1 upon I lambda, because see, negative minus of minus, it becomes plus. So the first term is written as 1 upon I lambda, and then minus of e raised to minus I lambda upon I lambda. And further simplifying, we get the final answer as 1 minus e to the power minus I lambda upon I lambda. So this is all about the first example. Now let's move on to the next example. Second example is quite interesting. So let's see what it is. Find the Fourier transform of f of x equal to e to the power minus mod x. Here the function defined to be e to the power minus mod x. Applying the definition of the Fourier transform to the given function, we get f of lambda equal to integral from minus infinity to plus infinity e raised to minus I lambda x f of x dx. Just putting the value of the function in this integral, we get f of lambda equal to integral from minus infinity to plus infinity e to the power minus I lambda x, and in place of f of x we are writing e to the power minus mod x dx. Now here we must note that the function e to the power minus mod x is an even function. Recall the Euler's formula e to the power minus I theta is equal to cos theta minus I sin theta. This formula we have learned in the 12th standard. So we require this formula to simplify our integral. So using this Euler's formula, we get f of lambda is equal to integral from minus infinity to plus infinity cos lambda x minus I sin lambda x into e to the power minus mod x dx. See, cos lambda x minus I sin lambda x is written in place of e to the power minus I lambda x. So the Euler's formula is applied here. So now just simplifying it further, we get f of lambda is equal to integral from minus infinity to plus infinity e to the power minus mod x into cos of lambda x dx, minus taking this I out of the integral sign, we get integral from minus infinity to infinity e to the power minus mod x sin lambda x dx. So now here we should note that cosine function is an even function, and we had seen that e to the power minus mod x is an already even function, and the product of these two, product of even and even function, is going to be even function. That's why here the integrand is totally an even function. Here also we should note that exponential function e to the power minus mod x is an even function, whereas sine of lambda x is odd function of x. Therefore, the product of even function and odd function turns out to be odd function. So friends, to evaluate these integrals, now we require to recall one of the property of definite integral that we studied. You can pause this video for a while and think about the property of definite integral that is required to be applied here. So please recall it. I hope you must have recalled the definition, that is property of the definite integrals. So that definite integral property required is this. Please note, integral from minus a to a f of x dx is equal to 2 times integral from 0 to a f of x dx if f of x is even, and it is equal to 0 if the function is odd. So now we are going to apply this property to our step. You can see here the step is present here, you can see. So this function, product of these two functions, is an even function, whereas product of these two functions is an odd function. That means the integrand here is an even function, and in the second integral the integrand is odd function. So applying this property, we get f of lambda is equal to 2 times integral from 0 to infinity e to the power minus mod x into cos lambda x dx, and the value of the second integral will be 0 as per this property, because the integrand is odd there. So now to next step would be f of lambda equal to 2 times integral from 0 to infinity e raised to minus x cos lambda x dx. Here in place of e to the power minus mod x, we have written e to the power minus x. It means that mod x mod x is written as x. The reason is the value of mod x is equal to x if x is positive. That's why we have written e to the power minus mod x as e raised to minus x. Now friends, we require one of the basic integration formulae in order to evaluate this. So we need to recall it. Recalling the formula of integration, that is integration of e to the power ax cos bx dx is equal to e to the power ax upon a square plus b square into a cos bx plus b sin bx plus arbitrary constant c. Arbitrary constant c is written because this formula is of indefinite integration, and here we are dealing with definite integration. So applying this definition, we get f of lambda is equal to 2 times e to the power minus of x upon negative 1 square plus lambda square. Because you see here, if you compare this integral with the formula, you can understand that the place of a is taken by minus 1, whereas the place of b is taken by lambda. Therefore we got e to the power minus x upon minus 1 square plus lambda square, and into a is minus 1, so minus cos of lambda x here, because b is lambda, plus b is lambda, here you can see lambda sin lambda x, and the limits are 0 to infinity. Now putting the limits, we get f of lambda equal to 2 times 0 is written here because e to the power negative infinity is 0. That's why putting the upper limit, we got 0 here, and then minus of putting the lower limit, that is 0. E raised to minus 0 would be 1 upon minus 1 square simplified to be 1 plus lambda square into cos 0 is 1, so minus of cos 0, so we have written minus 1 here, and then lambda sin lambda x becomes 0 when we put x equal to 0. Therefore the final answer would be f of lambda is equal to 2 upon 1 plus lambda square. So this is all about our second example on Fourier transforms. So this video content is prepared by referring to two popular reference books. One of them is Higher Engineering Mathematics by B.S. Grewal, and the other is Engineering Mathematics, a Tutorial Approach. Thank you friends.